Sebastian is going to give a talk titled "Gotta Prove Fast: Building an Ecosystem for Effortless Native Compilation of Tactics." So,
okay,
if you're ready, you can start.
Great. Thanks, Jesper. So yeah, this talk is on my recent work on making tactics go fast in the Lean4 Fear Improver. And to give you some context for that work, I'll start by quickly recapping some goals of the Lean4 project. First and foremost, we want to provide a fully extensible fear improving front end, this time much more than in previous versions of Lean. And in particular, we'd like to erase the boundary that existed between built-in syntax and tactics and so on, and once written by users. And we're already pretty close to that goal simply by rewriting all those built-ins and the entire Lean frontend and other parts of Lean in the Lean4 language itself so that they use the same API as user-written ones. And of course, to make that possible, we first had to make Lean itself an efficient and general purpose programming language. Okay, so with these goals in mind and our progress, would be great if user-written tactics were not only expressive as built-in ones, but also as fast, right? And people have tried to write complex tactics in Lean3, like resolution provers, and found that the interpreter performance was not satisfactory. All right, so how do we do it? So given that Lean is this interactive system where you can define a tactic and immediately use it inside the same file, you might think like a just-in-time compiler would be a nice solution, right? So yeah, and if someone could do that, I think that would be pretty nice. But just to us, it seemed like a huge project, and frankly, we have enough other projects to work on other parts of Lean. So we really didn't want to spend that much time on it. And even if it's working, I would have some doubts on like scalability, since like when we're spawning a new Lean process to compile each file and then redoing the chitting, so at least like to get something started, we really wanted to come up with a simpler solution. And I mean, we can already compile Lean code to native code. That's what we're doing with the Lean executable itself. So how about just reusing that ahead of time toolchain for tactics as well? That should be much simpler, right? Well, let's see. But also, any improvements we make on the toolchain during this work would also benefit people who simply want to compile Lean programs, not metaprograms. So that's a nice benefit. Okay, let's try to go with this one. And let's start by taking a look at the compilation pipeline in Lean4 as of today. So yeah, we have something like an elaborator that eventually takes the input and turns it into a sort of core terms, which can either be checked by the kernel, but they can also be transported to something I simply call the compiler that turns it into some sort of intermediate representation. This IR can be interpreted, and in turn, the elaborator can use the interpreter to drive tactic execution, much like in Lean3. So we have a nice little meta loop going on here, basically. But the new part in Lean4 is that the IR can also be passed to a C emitter, which does exactly what it says. It produces a simple C file that we can then put into a C compiler to create a native binary out of it. Okay, but given that, I mean, one simple approach would be to simply tell the C compiler to create a shared library instead out of our tactic file, and we could then load that back into the Lean process and simply tell the interpreter that whenever you see whenever you want to run a Lean function, but there's a native symbol for that function available in the process, simply run that one instead. And yeah, if we do that, then we have a bigger meta loop going on that actually can execute tactics at native speed. Okay, so this loading and running part is actually super simple. So in the remaining talk, all we have to worry about is how to create those shared libraries. And before I continue, just one more note on this talk. Like anything I'm talking about today is not affecting the trusted code base of Lean, which is, of course, the kernel. So anything a tactic produces, any proof term, still eventually has to go through that kernel, regardless of whether it was interpreted or created by a native tactic. Okay, so let's create shared libraries. And I mean, it's 2022. It can't be that hard, right? Like we have nice native languages like Rust that are easy to install. And depending on the platform, well, you only have to install the entire Windows 10 SDK afterwards, which can take a while to download depending on your connection. And it might not be much better on other platforms. Okay, so this is not great for our use case. Like maybe we can convince a computer scientist who wants to write in Rust that this is simply necessary to get started. But for, say, a mathematician that wants to use Lean and doesn't care about how their tactics get fast, this really should not be necessary. And in particular, we cannot require root permissions to install Lean and in a way that gets you fast tactics, because we want Lean, of course, to be usable on like arbitrary university machines that do not have these permissions. Okay. Fortunately, there are other languages like the more recent Zig language, which actually managed to provide a small self-contained native toolchain for like all the platforms we care about. So yeah, you can see here, if it's not too small, that like Zig releases are something between 40 and 60 megabytes. That sounds much better, right? So yeah, I got inspired by the Zig approach and basically copied it for Lean 4. And you might not be surprised to hear that this is based on LLVM. Because with LLVM, we have a C compiler, we get basic C headers. Turns out all the headers we need for compiling Lean files. We get a runtime library, compiler RT, and we get a linker which, since the very latest version of LLVM, actually has good macOS support. So this scheme would not have been possible a few months ago. And we get other tools we need for native compilation. Okay, so this is all out of the box. There are some parts that are not quite out of the box. So it turns out you really want to recompile LLVM from source if you want to distribute it. Like there's a dozen CMAC flags you probably want to customize. And then there's interfacing with the system C library, which is its own adventure on every single platform, including on Windows. But I won't get into that part for today. Okay, for now, let's simply assume we have a working native toolchain. So where do we actually create our shared libraries? So let's say we have a simple Lean project. There is a file that creates a tactic, defines it, and there are other files that want to use that tactic. And now our user tells us they want this tactic to be fast. So we put it in a shared library, right? And yeah, not just that file, but of course the dependencies as well. So yeah, so far so easy. If now another tactic comes in, we might not want to put it in the same shared library depending on the project structure. So yeah, let's make another library out of that. And then we just have to be careful if we want to load both libraries at the same time. We cannot create duplicate symbols. But I mean, that's easy to avoid, right? We just have to create another shared library for these common dependencies. So that actually sounds like a nice algorithmic problem, like partitioning Lean modules into nice big libraries that are not overlapping. We could solve that, or we do something much simpler and simply create a single static shared library per Lean module. And even for all of them, so the user doesn't even have to tell us anymore where the tactics are. Okay, I mean, that is very simple and definitely gets rid of the duplicate symbols, and we will have to see in the future if this actually scales, and may have to refine that scheme. But yeah, for now that's that works out for us. And in the future, I would especially like to fundamentally improve not compiling things we don't have to compile. By which I mean, just for another example, we might have a file that has a definition that is used by a theorem and another definition that is used by a tactic. And currently, Lean4 does not have enough information to decide that only the second definition has to be compiled to native code. What we could and want to do in the future is introduce something like the phase separations, such as in Racket, which could really tell us where the metaprograms are without the user telling us. So if, say, we had a separate meta namespace, which can only use other definitions in that namespace or import it into the namespace, then it would be much simpler for the Lean compiler to figure out what definitions have to be compiled. And yeah, on top of that, while we're trying to avoid compilation, would of course be very nice that if we change the body of a definition, say, that we don't necessarily have to recompile all the downstream files, especially if we don't want to inline that definition. And I mean, this is of course something that many other languages already provide, like GHC has the signature files, and it's simply a stronger sense of separate compilation that we don't have right now. Yeah, it's just, as far as I know, this has not really been tackled for fear improvers before, and there may be some special challenges in that. Yeah, but for now, let's summarize. So we can now in Lean4, if you check out the appropriate pull requests, compile tactics to native code effortlessly. And this is based on a coordination by the compiler, the build system, and the interpreter. And this is all based on a standalone LLVM toolchain, which is possible in 2022. It's just still not quite as simple as one might hope. In the future, we will definitely need to revisit some scalability questions about this whole approach when we actually have more libraries that we can test this on. For example, when Mathlib is completely ported. And we really want a better module system in the compilation unit sense, not the functor sense. So if you have any thoughts and ideas on that part, I would be especially keen to hear about them. Thank you.
Thank you. Let's see. Are there any questions yet? I see there's a question in the room.
Hi. Maybe it's because that I haven't followed the earlier work on this, but can you explain what the runtime for compile tactic looks like? Like startup of the runtime or that sort of stuff? Like how much gain does that really give you in terms of speed?
Sorry.
So what does it look like when you compile a tactic? Or like running that, how much, first of all, how much performance do you get from that? And also like starting the runtime for the compile tactic.
Sorry, so you're asking about basically the difference between native execution and interpretation for a tactic?
Right, yeah, because I wonder how much a compile tactic would have to know about Lean itself, and if that would cause any performance issues.
So the tactics are loaded into the Lean process, and so they can use any Lean APIs without particular overhead, apart from indirection. I'm not completely sure what you mean by the overhead of like knowing Lean. But so just to answer the general question, like we've been seeing like a 100x speed up of native execution compared to the interpreter.
Okay, thank you.
See, there's an online question here.
Yeah, maybe it's just to answer the overhead part. I mean, so there is, of course, the overhead of compiling the C code. There's the overhead of linking, but that's actually not all that much, even if you do it for hundreds of files. And loading the shared libraries is also basically nothing.
Okay, yeah, so there's an online question. I'll read it. So you mentioned that Flat suggests that macros are executed in different phase. Does this come into play into Lean 4? Or is there a connection with generalization of phases by starting and out?
Right. So I think the Racket work is basically directly applicable to us. I mean, we have macros that are very similar, that are inspired by Racket, and so the phases should apply to any kind of metaprograms, be it macros or tactics. I'm a little familiar with the other work. As far as I remember, part of it is about generalizing the kinds of phases you can have, right? Like a documentation phase and so on. That is definitely something that I could also see happening in Lean. Yeah, for a start, I'm not sure. We would probably focus on like a meta phase or on a tower of phases if we need something like that in Racket and see how far that will get us.
Okay. I think those are the questions then. So thanks again for the great talk.